In this video, we are recreating the Sanity System from Amnesia, The Dark Descent, from scratch in Godot 4. We are going to build a dynamic system that monitors the light level around the player. Standing in the light restores sanity, while lingering in the dark will slowly drive the player mad. We will also add an enemy that rapidly drains sanity if the player dares to look directly at them. As the player's sanity drops, a Distortion Shader will kick in, warping the screen and heightening the tension of your game. And just like the original game, solving puzzles or completing objectives will trigger a rewarding visual effect and restore some of your player's sanity. Now, the Sanity System is probably the most requested and most anticipated tutorial video of this horror immersive interactive controller series that I'm building. So let's go ahead and talk about what we actually need to be implementing in this video. So obviously I'm basing the Sanity System off of Amnesia: The Dark Descent. So let's talk about how the Sanity System in that game works and how we're going to be slightly changing it and using it as a basis for our project. In Amnesia: The Dark Descent, every 8 seconds of darkness, your character's sanity will drop by 1%. Now, if you use a tinderbox or if you complete a puzzle, that can increase from anywhere from 1 to 5%. Some puzzles, I think, will bump your sanity up by like 10%. Then there's also kind of the flip side of that is that if the player stares at a monster, their sanity will rapidly deplete. If they see, I guess they're called like spooky events, very scary things, blood, gore, things of that nature, your sanity will rapidly decrease. So all of this kind of goes into one big lump sum sanity system that we are going to be building. So Amnesia has a GUI attached to it in the inventory. We don't have an inventory set up, so we're just going to be using some raw numbers for the sake of our prototype. So let's talk about everything that we need to implement to get a sanity system like Amnesia. Now, the first and probably the most important part of this is a light detection system. Now, there are many different ways to do this. However, I have tinkered with a few of them. I found the best way is from a YouTube channel called GameDev Compass. Now, their video light detection in Godot 4 is exactly what we need. They're a great channel, so please go check them out, give them a little love for this video, because I'm going to be taking what they do in that 6-minute video and expanding on it and kind of explaining why and how that works. So essentially, that light detection system is going to give us a value between 0 and 1, where 0 is very dark and 1 is perfect bright light. However, like I said, Amnesia doesn't just treat darkness for sanity, they also treat other things, such as an enemy. So we will be implementing a dummy enemy. It won't have any AI. It's just going to be a red bean. And we're just going to implement a system to see, 1, if the enemy is on screen at all, and 2, if the player is staring directly at the enemy. Because if the player is staring directly at the enemy, we want the sanity to drop rapidly. And of course, the whole point of the sanity system is that it's supposed to be spooky. So once we reach a certain threshold, in our case, it'll be 50. Once the player's sanity drops below 50%, we need to start adding a distortion shader that kind of moves and kind of makes the screen all kind of blurry, and it adds a sense of difficulty and scariness to your horror game. And finally, we also need to work in the opposite direction. We need to be able to improve sanity. So not only will standing in the light improve your sanity, Amnesia also gives you sanity when you complete puzzles or certain objectives. So we will be using our simple switch to quote-unquote do a dummy puzzle, so that way when we pull the switch, we complete a puzzle, and our screen will flash green, and we will get a great increase in our sanity. Alright, so let's talk about this level. Now, in an effort to save time, I created this little dummy level here. All it is 4 CSG boxes for walls, a CSG box floor, some columns, and a little roof. And of course, we have our switch in here. I also added in a light pole asset. That is not necessary. Really, all you need is 4 different lights. I want the one in the middle to be the bright light that takes us to perfect brightness. And then I have 4 lights in the corner that are at a different brightness, so that way we can see how the different brightnesses affect our sanity system. And one of them I made a different color, so we can kind of talk about how color is also going to affect the light detection. So if you don't have an environment, it doesn't have to look just like this. You can just modify the world and directional light 3D environment and whatever environment you have right now. But of course, this doesn't look like a horror game, so let's make some slight changes before we start on the light detection. So this world and directional light 3D environment were just the default ones I added to the scene. It's pretty easy to make it dark, so let's go ahead and go into your directional light 3D node, and you're just going to change this from light and sky to sky only. Then go ahead and open the light panel and grab the energy and just drag that down to 0. Now in your world environment, go over to your inspector, get rid of it and create a new world environment. You're going to want to expand it, open up background and change from clear color to sky. And it wouldn't be a horror game with some kind of volumetric fog. So open up your volumetric fog, turn it on, change your density to 0.1, and then change your albedo to something pretty dark. Yep, that looks like a spooky horror game with 4 lights in the corner and a big bright light in the middle. So how are we going to detect light? So I'm going to do a quick demonstration of what we're going to do right now. So as you can see here, we have our player camera with our interaction raycast there. What we're going to do is we're going to add a secondary camera. As you can see here, it's going to be right where the player's head is, and it's going to be pointing down. That camera's only job is going to be looking at this kind of diamond shape here. And what we're going to do is we are going to take a snapshot of what our camera sees at any given moment, and we're going to do a slight algorithm to it. And the answer to that algorithm is how much light there is. So if you can imagine, we're looking right at this object right now. You can see that about half of it's shaded and about half of it is in light. So a value would probably be about 0.6 or 60% lit. Now, if you can imagine this omni light here that I'm using to demonstrate how the light would be in the scene, this can move around. Now imagine the omni lights right there. You can see almost the entire object is now bright white, meaning we're probably in a very bright, well-lit scene. Therefore, we're going to have a value around 0.8. Now, if I pull this guy, very far away, you can see there's almost no light on this object. It's very dark. Therefore, that would be a very low object. So we're going to create a secondary camera and this mesh instance. And every frame, we're just going to take a snapshot of what this mesh looks like at this given instance. And then we are going to perform a little calculation on that, and that's going to give us a value that's going to tell us how bright the character is. Because if you imagine this is our character being right here, it's a pretty good indication of how the light would be hitting our player from the various angles. So back in our player scene, you can see our head, eyes, and camera 3D. This is the camera 3D that the player will see as they play the game. What we need to do to add a secondary camera that can take a snapshot of the light information without kind of affecting our performance is we need to add what's called a sub viewport. So I'm going to left click on the player, I'm going to hit Control A, and we're going to add a sub viewport. And as you can see here, a sub viewport is an interface to a game world that doesn't create a window or draw to the screen directly. So this is going to create like a little isolated view of our camera and our mesh. So we're going to go ahead and add a node 3D, and we are just going to call this our light detection. And under light detection, we are going to add 2 things. The first thing we're going to do is add a camera 3D. We're going to rename that camera 3D to light camera. And again, under light detection, click it and hit Control A. We're just going to add a mesh instance 3D. Now we want to access all of these as unique names. So let's go ahead and right click all of them, everything except the mesh instance, because we don't actually need to do anything in code with that object. So we'll just go down the list, start at your sub viewport. You can see the default size of this is 512 by 512. We want to lower that to 16 by 16. The only reason we want to do that is because the smaller it is, the less performance intensive it is. And if you imagine us taking a screenshot every single frame of our game, that could become very intense very quickly. And frankly, the light detection doesn't need to be that accurate. So go ahead and lower that down to 16. I also turn off handle the input locally. And also go into your render target, update mode, set that to always. All right, so now for our camera, let's go ahead and left click on our light camera. Let's go to the transform. We're going to want to put this up 1.8 meters. That way it's sitting kind of right in the middle of our character's head. We want this rotated minus 90 degrees on the x-axis such that it is looking down. And once again, we don't need anything accurate, so we're just going to lower the field of view down to 20 because we're only going to be looking at a tiny little diamond. And we don't want this to be rendering 4,000 meters far. We only need it very, very close to the player. So just set that to 1 meter. All right, and finally, we're going to have our mesh instance 3D. So go ahead and left click on your mesh instance. we are going to create a new sphere mesh. We are going to make this a radius of 0.3. We are going to make this a height of 0.6. And we don't need it to be a sphere. We only need it to have 4 radial segments and 1 ring. And that gives us our diamond shape. Go ahead and give it a new standard material. We'll talk about that a little bit later. And we just need to drag this up to where our camera can see it. So let's set the Y to something like 0.85 maybe. Maybe set the rotation to -45 on the Y. And of course, what we can do is select our camera and hit preview. And that's what our light camera sees, and that's what we want. We want it to just see kind of a box of this mesh, just like that. And one more thing we need to talk about is the call mask. So you see these options here. If you're not familiar with these decide what your player camera can and can't see. So our mesh instance 3D here, you can see it's set on layer 1. And that means that if a camera has layer 1, it will be able to see it. The problem with this is that our camera 3D on our player can see everything in the game, right? So it will see this object. So if the player looks down, they will just see a random white cube on them. And we don't want them to see that. That's kind of why we have our light detection set up in a sub viewport. So what we need to do is we need to take this mesh instance, turn off layer 1, and just set it to something like 20. What we also need to do is on our camera 3D, turn off our call mask on 20. So what this means is that anything that is listed as layer 20, this camera will no longer see, and this will see it as well. Now we want to go ahead and leave our light camera picking up everything, just so that way any light data that's on a different layer, depending on what game you're doing, isn't really lost. All right, now we've probably missed something because I seem to miss something in every tutorial I do, but we're gonna go ahead and move on, hit the plus button, hit another node, and this one is just going to be a plain node on its own. And finally, we can go ahead and call this our sanity controller. We can save this scene under our player, I think is probably the best place to put it. We'll call this sanity controller scene. Go ahead and hit save. Then, of course, this is going to need a script. So we're going to go ahead and create the sanity controller script as well. So let's go ahead and start to code. All right, so I'm going to go ahead and go into my player. I'm going to drag the controller onto my player just so that way it sits right under our interaction controller. And we're going to go ahead and access that as the unique name. Now, what are we going to need? Well, the first thing we're going to need is our sub viewport. So go ahead and control right click or left click and drag in. And we're just going to call this our light detection viewport. We are also going to need our light detection 3D node, our kind of master node, if you will, of the camera and the mesh. And we're going to go ahead and just keep this as light detection. And then we're also going to need a variable that I'm going to call light level. This is going to represent how bright we are. Make sure you write an equal sign because I do have a habit of doing that. And let's go ahead and create our first function. So the first thing we need to do is create the ready function. And this returns void. And the only thing we're going to do in the ready function is set the viewport to only detect lighting. And we'll talk about what that means in a second. But go ahead and grab your light detection viewport, and you're going to set its debug underscore draw equal to viewport dot debug draw lighting. So if I go back into my sandbox environment here, and I go into 3D, you can see we have a lot of different, we have light, we have color, we have a lot of things. And all of the draw calls have to get all of the color and the lighting data correct. Now that's very expensive. Remember, we're just taking a snapshot of a cube every frame. We don't need all this information. So if we go ahead and look at our display lighting value, you can see things look a lot different. It's basically all bright white because we're all in sunlight, except for these little areas that are in the shade. Now for our light detection viewport, the only thing we care about is whether or not we are in darkness or if we are in light or any combination of the two. So this is going to save us some processing power and prevent the sanity controller from kind of slowing our game down too much. So back in our controller, we need to go ahead and add our process function. And in our process function, we are going to create a new function to set our light level. So we'll just call this get light level. Go ahead and copy and paste this and create it below. The light level is going to be a float that we're returning. So let's go ahead and light level. There we go. And this needs to return some dummy value while we talk about what get light level is going to do. So get light level is going to do a couple things. The first thing we need to do is we need to update our light detection's global position, and we'll talk about why we need to do that. We need to get a picture of the cube. We need to make that into a color value. We then need to get the lightness from that color value and return it. So let's start with the simplest of that. We're going to go ahead and take our light detection node. So remember, our light detection node holds our camera and our mesh, and we are going to set that global position equal to the parent global position. And in this case, the parent is going to be our player. Now that seems confusing because light detection is a child of the sub viewport. Now, this is where things get confusing even for me, because the sub viewport kind of treats everything under it as if it's its own separate game, if you will. So in reality, if this light detection is some kind of child of the player, the position should, in theory, always follow where the player goes. But once something's in a sub viewport, it's kind of like its own little niche. It's a new instance of something. So while we have a reference to the player, we need to actually set our global position so that way what happens is the light detection system doesn't eventually kind of get behind as the player moves forward. It's a little confusing, and sub viewports in and of themselves are very confusing. But when you do it this way, it makes things very efficient and prevents the game from bogging down. So now that we know the camera and the mesh instance are in the proper position on the player, the first thing we need to do is get the texture of the viewport. So we're just going to create a variable that we call texture. We are going to use the sub viewport, and that sub viewport has a built-in function called getTexture, and that's going to return the 2D image of what we're seeing. So if I go back into my 3D view, I grab my light camera and I hit preview. This right here is our texture. That's what we're grabbing with this line right here. Now we need more than just the texture, we need the color. So create a variable called color, and color is going to need to get the average color of the entire image. So we're actually going to have to create another function that we're going to call getAverageColor, and we're going to send it that texture. So go ahead and copy this and create a new function called getAverageTexture, which is going to take in texture, but this needs to be defined as a viewport texture. And this is going to return for us a color. Now, let's go ahead and take a step back and talk about what we're actually going to do here. So if we go into our 3D view, what we're going to have, it looks nice here, but remember, this is a 16 by 16 pixel image. We don't need all 16 by 16 pixels. We only essentially need one pixel that is the average of all of them. So we are going to take these pixels and we are going to downsize into a single pixel and return that value. So here in Paint.net, you are looking at a single frame snapshot of what our texture would look like. So remember, this is going to be running every frame. So let's say we're generating 60 of these a second. Here it's pretty dark, here it's pretty light, here it's in the middle. I was just on the border of where a light source was. So how do we get the average light just from this texture? Well, essentially what we're going to do is we're going to resize the image and resample it all the way down to 1 pixel. So you can see here, this resampling value here, I believe this is pronounced Lanczos
algorithm.
This is the best looking resampling. We have bilinear, bicubic, and nearest neighbor. Now, if you've made any 2D games, you'll know that nearest neighbor is really good for pixel art, so on and so forth. But essentially all we're doing is this, and that is it. There is our 1 pixel. That is the average color of the entire texture. Now, we're not going to be using Lanczos because that is probably, while the best looking, the least efficient. We are going to be using, I believe, bilinear. So essentially on this frame, We are going to resize this down to 1 pixel, and we are going to get this value here. So let's go back into the code and see what that looks like. So back here in the code, once again, we need to get the actual image from the texture. So we say var image equals texture.getImage. And now we just perform the algorithm I just described in paint.net. We do an image.resize. We want to resize it to a 1 by 1. And we want to use the resampling of bilinear. So now we have 1 pixel. All we need to do is return the single pixel, which is stored at 0, 0. So essentially we've just grabbed the image, we've sized it down to 1 single pixel, and then we are returning it. And make sure you put a colon there. So now that we have the average color, what are we gonna do with it? Well, color has a value that is referred to as the luminance. So we're going to go ahead and remove our dummy return statement, and we're going to return color.getLuminance. I went ahead and grabbed the luminance calculation. So essentially, your color is an RGB value, so it's multiplying the red by this, the green by this, and the blue by this. And that's going to give us our luminance. So what this means is we have a standard material that is white, and essentially that's not really going to affect the RGB at all, which is good. We don't want that. But just so you know, if you wanted to add a material texture to your mesh instance, that is essentially going to not break, but it will change your luminance. And that's all we need to get our light level. So let's go ahead and clean this up. And I want to go ahead and do one more thing. I want to go ahead and I want to open our GUI where our reticle is. Go into our 2D view, and I just want to go ahead and add a label. And we're just going to call this label for now debug. And then back in our script, we want to access that as a unique name and drag it in with our onReady variables. And the reason is I want to be able to print out our light level on the screen, so that way I don't have to zoom in on a tiny little output box when we edit, and I think it looks much nicer. So in our process function, we have just gotten the light level, so let's go ahead and update that label. So we have our debug text is equal to a string. Now the first thing I'm actually going to output is our FPS. This is very good when you're doing prototyping like this, because you want to make sure that you're not killing your performance, right? So we're going to go ahead and get the FPS, which you just do by engine.get frames per second. And then the next thing we want is we also want to display our light level. So do a /n, which represents a new line. And we're going to go ahead and just call this light level and add a comma and then print the light level. So let's go ahead and test and see if we made any mistakes. So running the game, you can see we are at 144 FPS. I believe that's because I have VSync on, but that's still a very good number to be at. And as you can see, we have a light level of 1 because we are standing in a bright white light. Now, if I go here right on the edge, you can see I'm about 0.4, and I can go into complete darkness pretty quickly. If I come over here into the red light, you'll see I'm at 0.79, 0.65, something about that nature. Now let me go ahead and run over to one of the yellow lights. You can see I'm about the same, 0.76, 0.78, so a little bit different. We do have an effective way of telling what our light level is, and it's not killing our performance. Okay, so now that we are able to accurately calculate the light level, we now need to apply that to some sanity variables so that way we can keep track of the player's sanity. So at the very top, we're going to add some new variables. I'm going to add a comment saying that these are our sanity variables. So the first one is our sanity. This is just going to be a float, and we are going to start the game at 100% sanity. We also need a variable called time since sanity change. That's going to be a float. Go ahead and set that to 0.0. Now we're going to create some constants because we don't want to accidentally modify these in our code. So the first thing we're going to do is const sanity drain interval. And if you're curious why these are all caps, that's the standard operating procedure for constants. This is also a float. And at the start of the video, I told you that Amnesia does their sanity drain once every 8 seconds. So we would do 8.0. For the sake of the tutorial, I kind of want to demonstrate things a little bit faster. So I'm going to set it to 25% or 1/4 of a second. We next need our darkness threshold. If I spelled this right. I believe it's OLD. This is also a float, and we're going to say that darkness is 0.3. And what this value means is that anytime the light level in the top left is above 0.3, we're not going to be draining sanity. However, once we are below 0.3, like right here, we're officially in darkness, and we should start draining sanity. You could complicate it and kind of have your sanity drain rate based on the amount of darkness, but this is a much simpler implementation, and we can always improve this in the future. So the next thing we need is our sanity regen target. This is a float, and we're going to set this to 51. So what this means is if our sanity is at 25 and we step back into the light and it starts to kind of tick back up, where should it stop? You could set it so it resets all the way back up to top sanity, but I believe Amnesia doesn't do that. I think Amnesia only takes you up so far. So we're going to do 51. And the final we need is our sanity regen rate, which is how fast we are going to regen our sanity. And a good way to do this is set it to the inverse of the sanity drain interval. And that should make things nice and clean. So down in our process function, we're going to create a new function call, and this is going to be update sanity, and we are going to send this delta. So go ahead and copy this, create this function down here, and this, I believe, should return void. We're just going to update our sanity value. Let me hit enter so it's in the center of our screen. So remember, delta is the time difference between the last frame. So we need to keep track of that with our time since sanity change, and that's going to plus equal delta. And so our time since sanity change is going to make sure that we are applying our sanity drain correctly. And so we need to update our sanity in two different ways. So if our light level is less than or equal to our darkness threshold, then in this case we are in the dark. And if we are in the dark, we need to drain sanity. So how are we going to drain sanity? Well, we need to check if our time since sanity change is greater than or equal to our sanity drain interval, and our sanity is greater than 0.0. Now, what is this saying? So remember, our sanity drain interval is 0.25. And the time since sanity change just represents the change between the last frame. So we need to make sure that we're not changing our sanity based on the frame rate, we're changing it based on time itself. And of course, we need to make sure that our sanity is greater than 0, because there's really no point to having negative sanity, because once it hits 0.0, you're either dead or something else awful happens. All right, so if at this point we are draining our sanity, we should take our sanity, we should minus equal that to 1.0, so drain a sanity point every drain interval. Remember, for Amnesia, that'd be every 8 seconds. We're going to take away a sanity every 1/4 of a second, which is pretty fast, but once again, that's for the tutorial. We want to clamp our sanity between the value of 0.0 and the value of 100, because obviously we don't want negative sanity, and we don't want to regen sanity past 100. And then we want to reset our time since sanity change back to 0. So essentially, this delta value is going to be like 0.08, 0.07, 0.07, 0.06, 0.08, and we just need to make sure that we're only draining that sanity if it's been at least 1/4 of a second. And if it has, reset the timer and keep draining sanity if we're past the darkness threshold. Now, the other instance where we need to update sanity is if we are in the light. So if our light is not lower than darkness, we do want to slowly regen sanity, What you could do is you could have a lightness threshold where maybe you need to be in at least 70% light to regen, and if you're between 30% and 70% light, you don't do anything. For the sake of the tutorial, we're going to make it nice and simple, and we're just going to say if our sanity is less than our sanity regen target. We also need to check if, make sure you put a colon on the end there. We also need to check if our time since sanity change is greater than the interval, because once again, we only want to affect the sanity every so often. So if both of these are true, we want to say sanity plus equal our regen rate times our sanity drain interval. And we'll talk about why that is in a second, because that's the most important calculation here. And of course, we also need to clamp this value between 0.0 and the sanity regen target. So in this case, we want to clamp it between 0 and 51 because that's the max we want to regen at. And just like above, we need to take this and set it back to 0. And let's go ahead and add one more function just for the sake of making the display more interesting. Now, Amnesia has a little GUI and a little brain, and when you hover over it, it will tell you your sanity state. We're not going to do any kind of GUI in this video. That's kind of beyond the scope of this, but we are just going to do a little text update. So let's go ahead and create a function that's called getSanityState, and this is going to return a string. And this is exactly how Amnesia does it. I'm just taking it right out of the box. If in Amnesia your sanity is greater than 75%, your sanity state is referred to as crystal clear. If your sanity is greater than or equal to 50, your sanity is referred to as a slight headache. If your sanity is greater than or equal to 25, it is referred to as head is pounding and hands are shaking. If your sanity is greater than or equal to 1, it just kind of funnily returns ... And then, of course, finally, it will return unconscious. Now, I don't think you'd actually be able to see this one. I think the player passes out. But we're going to return these values up here in our debug text. But we are going to change this a little bit. So if you're new to coding, this may not make a lot of sense to you, but I promise I will explain it. So let me go ahead and comment out that debug.txt. Now remember, debug is just our label that displays on screen. We are going to set our debug.txt, and this is going to be a little confusing, but stay with me here. So the first thing we want is our FPS. We'll say %d. Then we want /n to create a new line. Then we want our light level, and that's going to be %.2f. Then we want another line. Then we want our sanity. That's going to be another %2f, or 0.2f, excuse me. Then we're going to do another /n. We're going to call this state. That's going to be %s. And then finally put a %sign and then open some brackets. Now here, we still want to keep our frames per second to make sure that we are not killing the performance of our game. The next thing we want is our light level. The next thing we want is our sanity, which remember, that's a float. And then finally, we want to call that function that we just wrote, getSanityState. So what are these lines here, this %d, this %.2f? So this %d is just going to replace this with this engine.getFramesPersecond value. So when Godot reads this, it'll see right here, it's like, well, I need a value, right? So it's going to look at this array here and find the first value and populate it there. Now you can see here's light level times %.2f. Now that is saying that it wants to substitute in this float value here. So light level 0.2f, it's going to substitute in a float. And that's the exact same for sanity because sanity is also a float. And then finally, our state is %s, which tells Godot that it should substitute in a string. So it's going to call getSanityState, which will return one of our strings. And all of this should output to our label. So let's go ahead and test and see if we missed anything. So running the game, you can see we have good FPS. We are currently in light level 1. We have 100% sanity because we just started the game, and our state is crystal clear. So let's go ahead and run over here, and you can see our light level is at 50. Now that it's below 3, our sanity is slowly going to drain. Now, like I said, Amnesia will do this a whole lot slower. It's only a sanity point every 8 seconds. We are doing this very, very quickly, so we want our sanity to drop. So let's go ahead and let this run down to about 51. So here you can see our state changed to a slight headache once our sanity dropped below 75. And now that we drop below 50, our head is pounding and our hands are shaking. I'm now noticing the typo in shaking. And now that our sanity is below 25, our state is just ... And now at 0, we are officially unconscious, which is probably a game over. Now we just want to test to make sure our sanity is regenning properly once we are in light. So now that we're in light, you'll see our sanity starts to increase, and our state should be affected as well. And we should keep going up and up and up until we eventually stop at sanity level 51. So let's make sure that works. All right, there you go. So now that we have that, our sanity regen and our drain looks to work properly. Let's just go ahead and make sure that this also works in light. So you can see here, we'll drain a little sanity in the dark, run back over to the light, and it goes back up. Let's make sure this also works on the red light over here, and it does indeed. So now we have a very flexible sanity system. And as you can see, the only problem with this is that all we have right now is a text sanity value. We need to report to the player somehow that they are losing sanity, and that is a very bad thing. So we need to work on a little distortion shader that is going to mess up the player's view and cause some problems. And to do that, we're just going to go ahead and exit out of the game. On our sanity controller here, hey y'all, it's editing me here. You should not be adding the following sprite 2Ds to the sanity controller that's in the player. Those are only local to the player. In hindsight, you should really be adding these to the sanity controller in its own scene, the scene that's up there right next to the sanity controller. It doesn't really matter because you're not really going to have a second player in this kind of game. However, if it was multiplayer or if you were going to reuse a sanity controller for some other scene, you would need to make sure that these distortion sprites and the shaders that we're building would go onto the reusable scene. So just go ahead and do that. If you just want to follow the tutorial, you probably won't run into any issues, but just so you know that I know that you know that I know. Sprite 2D. And the reason we're going to do a sprite 2D is because we want it to affect the screen, the entire screen. Now we can see our sprite here. We need a texture, and it doesn't really matter what the texture is because we're going to be setting it in the shader. So I'm just going to grab the icon.svg and go ahead and drag him on there, and just go ahead and stretch him so he fills the entire blue box there. So like I said, this image will not appear. We are going to actually define what the texture is in the code. So now that you have this, just make sure that it goes all the way around the entire screen. And also make sure that we call this distortion and access that as a unique name. So we've done shaders before, but once again, I'll show you how to do it. Just go ahead and create a new shader material, open it up and create a new shader. This one is going to be called Distortion Shader. And we don't want this in the player. We want this, I believe we have a shaders folder. We do. Go ahead and put it in that folder and go ahead and hit create and then click on it so we can open it up in the shader editor. Now, just like previous videos, I will leave this shader code in a pinned comment or the description or something, so that way you guys can get it for yourself. I'm not going to write out shader code. It's a little more verbose, and this is more geared towards newer players. I will recommend checking out the Godot shaders website. There's probably some better distortion shaders on there that may fit your game better, but regardless, go ahead and just copy the distortion shader from wherever I put it and slap it in here. Now, you'll see that nothing is really happening, and that's because we need to go into our shader parameters and set some things up. So you'll see I have two noise textures, an offset, and then the distortion strength. Essentially what we're going to do is we are going to create two noise textures that kind of fight each other, and they're going to distort the way the screen appears. So on your first noise texture, just go ahead and create a new noise texture 3D. And then under noise, create new fast noise light. And then this is all fine. You can sit here and tinker with these settings. I think I'm just going to kind of leave them be and just kind of randomly change them. That looks good to me. Now on our second noise texture, let's go ahead and create another new noise texture. We want our noise to be a new noise light, and we want to make it a different one. Let's say simplex or maybe cellular would look good, and kind of change it up. So as you can see here, we're essentially having two different noise textures that we are going to have fight based on the distortion strength of our shader. And it may seem like nothing is actually happening right now, and that's just because this is affecting a kind of a blank image. If you run the game, you'll see that this is what our distortion shader looks like at our current strength, and you can see that's going to give you a headache pretty quickly. So go ahead and hit escape out of that, and let's go ahead and apply this distortion shader based on our sanity level. So back here in our script, we need two onReady variables. The first one is a reference to our distortion. We're just going to leave that as distortion, and we're going to go ahead and write our other one. So we're going to create an onReady var, and we're going to call this distortion material. That is a shader material, and we are just going to set that equal to the material value here. And this is what we're actually going to use to affect our screen. So go ahead and go back down into your process function and add another function that we're going to call update distortion. And update distortion is going to get the sanity level that we just updated here. So then down here at the bottom of the screen, let's create a function called update distortion. That's going to take in a float called sanity, and I believe it's just void. So the first thing we need to do is create a little local variable that is a float called distortion. And then once again, you can decide for yourself, but I want the player's sanity to slowly, or I want the screen to slowly start to mess up with this distortion shader when the sanity starts going below 50. However, I don't want, let me go ahead and just comment that out. I don't want the screen to look like this when they're at level 50 sanity. This is what it should look like when they're, down at 1%. So we need to build a little curve that's going to make this a lot cleaner. So if our sanity is below 50, we want to start distorting the player's screen. So let's go ahead and create a variable, and we're just going to call this t. Now t is just representing a like a time on a graph, because we're going to build a little curve through code. And so we're going to set this equal to 50 minus sanity divided by 50. So if our sanity is 50, so we're just now being affected by the curve, 50 minus 50 is 0, 0 divided by 50 is 0, so therefore we want to be at the very start of our curve. And if our sanity is at 0, which is the lowest it can go, 50 minus 0 is 0, 50 divided by 50 is 1. So this value t is going to give us a value between 0 and 1 that we can apply to our curve. So now here is where we are going to do our calculation. So we're going to say that t is equal to pow of t to 2.5. And then we're going to say that our distortion is equal to t times 0.05. And this scales to the max distortion. So this curve is going to start very slow, and then it's going to end fast, which means that once you're below 50, you're going to only see a little tiny bit of distortion. But once you're down to like 10, 9, 8 sanity, it's going to ramp up really quickly. So I realize this is probably better with a image. So down here, this is where our sanity is 50. So there's going to be almost no distortion effect at all on our screen. Right about here is where our sanity is probably about 25, and that's probably where you're going to start seeing some major effects on your screen. But as you get up and up and up, the sanity distortion is going to get worse and worse more quickly. So that encourages the player to say, hey, your sanity is getting really bad, you should find some light. And so now that we know what level our distortion is at, we actually need to apply it to our shader. So we're going to grab our distortion material, and we're going to call set shader parameter. Now the shader parameter is down here, this distortion strength at 0.1, and we're going to say distortion strength, and double check your spelling because it's important that those match. We want to set our distortion strength to our distortion value that we just got here. And for the sake of this demonstration, I'm actually going to lower our drain interval even more down to 0.1. So if you go ahead and hit start, you can see that we don't have any distortion on our screen. And if I go into darkness, nothing's going to happen until we drop below 51. And once we're below 51, you'll start to see a little bit of distortion right there. And it will get worse and worse and worse until we're at full distortion. Now, if I come back in, the light will bring us back up in our sanity level and we won't see as much distortion. I go back into the darkness and you can see that it reapplies. So now we have some kind of sanity distortion. Now, if you want a different amount of distortion based on your time, all you have to do is edit what sanity you want the distortion to start applying at, and you can also create your own curve to affect it as well. All right, so now that we have our light detection and our sanity system up and running with a distortion shader when our sanity gets too low, let's move on to the next topic, and that is lowering the player's sanity when they are looking directly at an enemy. So obviously the first thing we need for this is an enemy. So let's go ahead and do that. I'm just going to click plus, a new 3D scene, and we're going to go ahead and change this type to a static body 3D. Now, if you have an actual enemy in your game, this is probably not going to be a static body 3D, but we are just going to demonstrate the principle of what you would do for an enemy. So I'll go ahead and rename this to enemy. We're going to add a mesh instance and we're going to add in a collision shape. These are both going to be beans, so make sure you choose your capsule mesh. Capsule shape 3D, and then on the mesh, go ahead and add a material override and change its albedo to be red. I'll just do full bright red. So this is going to be our enemy, nice and simple. It's just kind of a placeholder so we can tell if something called an enemy is on the screen. And the way we're going to do that is, if you already have an enemy for your game, all you need to do is ensure that your enemy is going to be in a group that we're going to call enemy. So if you're not familiar with groups in Godot, you can attach basically tags to your scene. And these tags will list like enemy, ally, object of interest, etc. And when we get the enemy object, we can essentially ask it, hey, are you an enemy? And so if we have it here as an enemy, we can go ahead and save. And we're just going to, we should probably create a new folder for this. So we'll call this enemies is fine. Create a new folder and go ahead and save the scene. And I believe that's everything we need for the enemy. All right, so now that we have our enemy, let's go back into our sanity. Yeah, let's do it in our sanity, obviously. We are going to drag our enemy scene and we're just gonna put him in the corner over there, just like that. So if I go ahead and hit save and we start the game, we can see our enemy lurking over there in the shadows. And that's what we wanna see. So now let's go ahead and go back into our sanity controller and into our script, and let's write some code to see if we can tell when an enemy is on screen. All right, so back here in our sanity controller script, we are going to create a new function, and our first function is going to be is enemy on screen. This is going to take in an argument of enemy, which is just a node 3D. And this is going to return a Boolean because it's going to be a yes or no value if the enemy is on screen. So at the very bottom, just write return true. So what are we going to do to tell if an enemy is on screen? Well, we need to get the viewport, which is the image representation of our screen. We need to know the camera position, where the player's camera is. We need to know where the enemy is. We need to calculate which way the camera is facing. And then we need to get the distance between where the camera is in the center of the screen and where the enemy is. So let's start out with what we can get. I think we need to get a reference to our player camera. We do indeed. So let's go into our player here and let's go ahead and open the head and just drag in the camera 3D here. That should be referenced as a unique name, and we are going to change this to the player camera just because we also have the sub viewport here, and if you make any changes and have to add that camera in, it could get confusing. So back here in our function, now that we have our player camera, we can do some logic. So the first thing we need to do is get our viewport. So we're going to create a variable called viewport. It is of type viewport, and that is equal to the player camera dot get viewport. And then the next thing we need to know is the screen size. So screen size is a vector 2 holding our x and y value, and that's equal to our viewport dot size. Not size changed, just size. All right, now we need to have 3 variables. We need to know our enemy position, our camera's position, and the difference between the two. So we need a variable, enemy position, which is a vector 3, and that is equal to enemy, which is the argument we passed into this function. That is equal to its global transform dot origin. We need to do the same for the player, but in this case it's more so the camera. So camera, in the exact same way, call the player camera dot global transform dot origin. And then finally, we need to know the difference between the two, which I'm going to refer to as to enemy, as the distance between the enemy. Now, this is a directional vector, which tells us this is enemy position minus the camera position. This is a directional vector from the camera to the object. And lastly, we need to get the direction of the player camera. So we're going to call the opposite of player camera dot global transform dot basis dot z. And if you remember the episode of the door, if you're following along with the series, this is what we did to figure out which side of the door we're on. So the basis of z, if I come in here, the basis of z is this axis here, right? So we just need to know which way is forward and which way is behind the camera. Now we are going to do our calculation. So we are going to check if forward period dot to enemy, and I'll explain what this line is doing in a second, to enemy is less than 0.0, return false. So essentially all we're doing here is we are checking if the object is behind the camera by using the dot product. So this dot product will return a negative or a positive value. If it is negative, that means the object is behind the camera. So essentially, here, we are cutting where the enemy could be in half. In fact, let's go ahead and look at sanity here. So for instance, our camera is looking, where is it looking? It's looking at this top half. It's looking up here, and it can't even see the enemy. So we don't even want to bother doing any more calculations if we know the enemy is behind us. So after that, we now need to get the screen position for the player's camera. So we'll call this screen position. This is a vector 2, which is equal to the player camera dot unproject position, and we are unprojecting the enemy position. Now, if you remember the door video again, this is taking where the enemy position is in global 3D space, and it's telling us where is it relative to the player camera, meaning, you know, where is it on screen. So if I go back into my sanity here, and I just grab the player, and I rotate them around 180 degrees, so now that they're looking at this half of the screen, it is possible they could see the player. In fact, if I run the game and I look like this, the player is on the screen. However, if I'm over here, the player is technically in front of me, but they're not on the screen. So we need to check if this screen position, quote unquote screen position, has the enemy in it. So the first thing we're going to do is we're going to check if screen position dot x is less than 0.0, or if the screen position dot y is greater than, or the screen position of x is greater than the screen position or screen size dot x, excuse me. And what this line is saying is the enemy so far left off our screen that we don't actually see them, or is the enemy so far right off our screen that we don't actually see them? So I'm going to go ahead and hit return, return false. We're going to go ahead and hit play. So right now, the enemy is so far off the far right of my screen that while they are in front of me, and the game does know about them, they're not actually on the screen. So in that case, the enemy is not on screen, we want to return false. So you can go ahead and copy and paste that line and paste it down here as well. And you just want to swap these out and change them to their Y value, right? Because the enemy could, and in this case, we're going to go ahead and run the game again. The enemy is in front of me, they're on screen, but if I look down, they would be above where my screen is. And if I look up, they would be below where my screen is. So if we go over this, we did calculations. If the enemy is behind us, we don't want to bother doing this calculation because they're definitely not on the screen. But if they are quote unquote in front of us, we need to make sure they're within the bounds of the screen. Any other situation, we want to return true because that means the enemy is on screen. Now, we don't necessarily care if the enemy is on screen. We necessarily care if we are looking directly at the enemy. So we're going to write another function that is func isEnemy in view. IsEnemy in view is also going to take in an argument for the enemy as a node 3D. And it's also going to take in a float value that we are going to call tolerance degrees. This also returns a Boolean that will be true if the enemy is being stared at, essentially, and false otherwise. So let's go ahead and talk about what we need here. So the first thing we need is these two variables from up here, the enemy position and the camera position. We need to keep these. And you can go ahead and just put a return false at the very bottom is probably the simplest way. We now know where the enemy is and we know where the camera is. We need to make a similar calculation. I'm going to grab the var to enemy again because we need a similar calculation to this. However, the difference is we want to do dot normalized. And the reason we want to normalize this is because we are going to be doing an angle calculation, and that'll make more sense in a bit. So this is a vector pointing from the player camera to the enemy. Let's go ahead and make sure we spell that right. Now we need to do a similar calculation to forward. So let's go ahead and just grab forward, paste it here. In fact, I think it is the same calculation. So we can go ahead and keep this. So once again, this is the camera's forward direction. And then finally, we need to compare these two angles. So let's take a variable, call this angle in degrees, and this is going to be a float. Now this is going to be a little confusing, and I'll explain it as we do it. So we're going to do a radian, 2 degrees, and we are doing the arc cosine, so A cos, and we are doing that with our forward direction, and we're taking the dot product to the enemy. And then this is going to give us an angle. So we're going to return if our angle degrees is less than or equal to our tolerance degrees. So here in Paint, I just took a little top-down snapshot of the game. So right here in the middle is where the player spawns. And I don't know if you're going to be able to see the enemy because YouTube compression is kind of annoying. But there's the enemy up there. So here we have the player, and here we have the enemy. So we have two calculations. We have the forward direction of the player's camera, and we have the direction from the center of the player camera to where the enemy is, even though we're not actually looking there. So let's say the player is looking in this direction, right? So they're looking that way. And then let's say we actually know this, is that the enemy to the player is here. So you don't have to know or understand the calculation of the arc cosine with the trigonometry here, but we have a triangle here. And right here where the forward vector and the to enemy vector are, we can calculate this angle here, this little orange angle. And this is going to return a value that we can compare against in tolerances. So for instance, in this example I've drawn here, you can see the player really isn't looking directly at the enemy, so we don't really want to lose sanity. This could be the player sitting on a corner and just kind of keeping the enemy in their peripheral vision. However, if the player is looking right here and the enemy is right there, you can see that our angle there is very small. And so that's what we're going to consider the player looking at the enemy. I've played Amnesia a little bit, and it's kind of funky with their calculations on what is and isn't looking at the enemy. They typically do if it's on screen, unless you're like behind something. So it's a little janky, but this is going to work for us. So back here in the code, let's say our tolerance is something like 10 degrees. That's a very small angle. If the player is looking and the angle is, let's say, 9 degrees, then they're going to be within the threshold to say, hey, they're actually looking at the enemy. So maybe they're just looking barely to their right. We're going to say they're looking at the enemy. But we actually need to call these two functions. So let's go ahead and go up here. And after we have updated our sanity, we need to do for enemy in getTree dot get nodes in group enemy. And the reason we're doing this is because this is going to get every single node in the scene tree that is in the group enemy. So remember, our enemy is in that group. That way, if your horror game has multiple different enemies, maybe you have 3 or 4 monsters on a single level, all of them will be accounted for in this sanity calculation. So the first thing we want to check, we want to see if is enemy on screen. And remember, this is the first method we wrote, where we only care if they're on screen at all. So for my game, we're not actually going to do anything for this. But if you wanted to do like a light distortion or maybe some kind of panic on the player, this is where you would call that method. And of course, if the enemy is not on the screen, we don't even want to bother checking if they're in view because they're clearly not in view. So we're just going to check the next if statement. So if the enemy is in view. So if the enemy is on screen, then the enemy could be in view. So we're going to check that. And remember, we are going to say enemy, and I'm just going to put a hard-coded value of 10. In fact, let's not do that. If we have the constants up here, we can just go ahead and create a constant. Const enemy view range. This is going to be a float, and I think I gave 10 in my example. Yeah, okay. We'll do 10 there, so go ahead and copy that down. So we are going to check if the player looking at the enemy is within 10 degrees, and if it is, we want to what do we want to do? We want to drain our sanity. We need to create a function to drain sanity because we don't want to just modify it here. We'll say that. And I'll show you why we're going to do that in a second. So let's go ahead and write some functions to add sanity and drain sanity. So create a function that is called drain sanity at the bottom. We are going to give it an argument that's called amount. That's going to be the amount we drain the sanity by. That is a float, and this returns void. So we're going to go ahead and say sanity minus equals amount. And then we need to clamp this value because we don't want to go below 0 in our clamp. So clamp sanity between 0 and 100. Oh, and make sure you have a colon here. And of course, we want to do the same in the other direction. So just go ahead and copy and paste this. Change drain to add, and instead of minus equals amount, we are going to add it. So we can drain sanity by any amount and then ensure that it's clamped and it won't go below 0. And we can do the same with add sanity. We can add any amount and make sure that it's clamped so it doesn't go above 100. And what we could do is you could tie this in with the interaction system where maybe the player picks up some, like, I don't know, Xanax off the ground, and then they take that and then they have some kind of sanity boost as well. So that should solve this problem up here. So if the enemy is in view, we want to drain the sanity by delta times 8. And remember, we need delta because we only want to drain our sanity relative to the frames in the game. So if this was just 8 and we had a lag spike, it wouldn't be accurate. And 8 is just a hard-coded value I put in because when you are looking at the enemy, I want your sanity to drain really, really, really fast. So let's go ahead and test and see what this looks like. If I run the game, you can see that I can have the enemy on my screen and I can kind of keep them in the corner of my eye. So I'm not losing any sanity. However, as soon as I look up, you see I'm not even looking directly at the enemy, but they're clearly in my line of sight, and my sanity is going to drain rapidly. Look at that. It is plummeting right now. And the distortion effect will still exist, and even at completely 0 sanity, if I just turn away and the enemy is no longer on screen, I will regain my sanity. And that's how you implement causing an enemy to drain your sanity in our controller. All right, so now I hope that this is all making sense to you. We only have one more feature to implement, and that is if you pull a lever or complete some kind of puzzle, we want your screen to flash green. Yay, you've done something, and we want that to increase your sanity. So let's go ahead and look in our player, and let's go ahead and add another sprite 2D. And so instead of distortion, this is going to be called puzzle complete. So go ahead and select your puzzle complete. access it as a unique name, go into your inspector, and once again, we're going to do the same thing we did with the previous shader. Just drag the icon over it and stretch it so that way it takes up at least the whole screen. And we're going to go ahead and set that to be invisible just for the moment. All right, and we're going to do the exact same thing that we did for the distortion shader. We're going to go into the material. We are going to create a new shader material, and we are going to create a new shader. So once again, go to your shaders folder, and we are going to call this, let's say, puzzle complete. Go ahead and open that and create. Double click on it so that way it will open in our shader editor. And this one is actually fairly simple. So I'm going to copy and paste. And once again, this will also be in a pinned comment. I'm going to quickly explain what this is doing. So we're getting the screen texture, which is what is on screen. And we're creating a float value that is clamped between 0 and 1. That is the alpha. If it is at 0, the alpha is at 0, which means that we won't see it at all. If the alpha is at 1, that means we should see it. So in fact, go ahead and make puzzle complete visible. And you can see here, if you go up and down, you can see that at 0, it's nothing, and at 1, it's completely green. So we are essentially getting the screen color. We are creating a green tint with this alpha value, and that's what we're setting the screen color to over time. So in code, we are just going to modify this alpha value if we have completed a puzzle. So it's important that you keep this toggled off, because if this is toggled on, it will overwrite the distortion shader and you will never see your distortion. So what we'll do is when we get our puzzle complete, we will turn on the puzzle complete, we will flash green, and then we will turn it off. So make sure that's turned off as we go into our code. All right, so back here in our code, we are going to need an onReady variable for our puzzle complete. And I'm actually just going to go ahead and call this flash sprite because it's going to flash on the screen. And the next thing we're going to need is you can go ahead and copy the distortion material one. But instead of distortion material, I'm just going to call this flash material. I think that makes sense. And that's going to be equal to the flash sprite material. All right, and then we're going to go ahead and come down here, and at the bottom of our script, we're going to create two new functions. We are going to create a func on puzzle complete. On puzzle complete is going to take in a few values. We could hard code these, but I like kind of exposing them as arguments because different puzzles could kind of have different reactions. We are going to call this first one flash duration, and it's going to be a float, and we're going to set its default value in the argument to 0.1. And then we also want another one called fade duration, which is going to be a float that I'm going to set to 0.5, which is how many seconds it'll run for. We want it to be very quick. This is going to return void. Now, remember what I just said. The first thing we want to do is take our flash sprite, and we want to set its visible property equal to true, which is the same as doing that. Now that it's true, we want to take our shader, what did I name it? Flash material. Take our flash material, and we want to set that shader parameter, and we want to set its alpha. We want to set its alpha to 0.5. And the reason for that is you don't want it to flash bright green on the screen, but 0.5 right there is enough to be like, hey, green is good, you did something good. Now, the next thing we're going to do is we are going to create a tween. So that's var tween. We're going to call getTree.create tween. Now, tween is essentially very similar to lerp. They both interpolate over time, and there's pros and cons to each. And typically when you are iterating over things like your speed, your acceleration, linear interpolation, which is what lerp does, linear interpolation is better. However, when you are doing graphics, tweens seem to be a little bit better. That's kind of a more in-depth discussion. For the sake of this video, we are just going to move on, mainly because I cannot say tween or linear interpolation without fumbling over my speech. So we are going to tween, which is just interpolating. We need to set the interval for how long we're going to interpolate, and that's just equal to the flash duration, which is this argument we set here. Now we need to set the property that we are actually iterating over, and the property is the flash, not the flash duration, the flash material, and we are iterating with the, what is it? No, it's shader parameter / alpha. And so this shader parameter / alpha is referring to right here, shader parameter alpha value. We want to, put a comma at its final. It should be at 0. We want it to go back to being invisible, and we want it to last for the fade duration. And then finally, we are going to add a callback, which will run at the end of the tween. So this is going to be a callable. It's calling on itself, which is the class that we're currently in, is where we're going to write the method on flash complete. So what are we doing here? So right here, we create our tween, and we are setting the tween interval for the flash duration. So that means that when we set this to 0.5 right there, we are going to stay at 0.5 for a full 1/10 of a second. After 1/10 of a second, we are going to tween the alpha back to 0 over half a second. So the flash duration is how quickly we get there, and the fade duration is how fast we go back. So we want to put it on screen and let it simmer out. Now, the reason we want this callback is for 2 reasons. The first is, let's go ahead and write this. On flash complete, we don't need any arguments. We're going to do 2 things. The first thing we're going to do is take the flash material, and we are going to set the shader parameter, which is alpha, and we're going to set that back to 0. This is similar to the lerp function, where you need to make sure that even though you're getting close to finishing, you need to hard set that value back. So we want to be sure the next time the player completes a puzzle that this is starting back at 0. That doesn't really matter when it's a simple green animation over a second or a half second, but we want to set this up for you to do any kind of tweening. So it's always good to set that back to 0. And then the final thing we want to do is set the visibility back to false, so the next time the player loses sanity, the puzzle complete is not overwriting it. There are our 2 methods. We set the flash sprite to visible, we tween over so it'll go up quickly and then back down, and then we reset it back to 0 and we set it to false. Now, how are we going to call these methods? Well, let's go ahead and go into our sanity, and I've had the podium switch here since we started. And on the podium switch, I've just created a dummy little node puzzle complete, and there's no reason for this node to exist other than for it to have its own little script. So let's go ahead and create that script, and we can just go ahead and call it puzzlecomplete.godot. Let's go ahead and put it in our scripts folder, however. Scripts, puzzle complete, and create. So here we have this script. Now, what this script is going to do is it's essentially just going to sit on the switch and monitor its percentage. So it's essentially the switch script. But we need a few things. The first thing we need to know is we need to get a reference to the sanity controller, which is a node. And of course, we need to know if we completed pulling the switch. So that way the player can't just complete the puzzle over and over and over again to boost their sanity. And similar to the way we did the interaction controller, we're going to create a function that I'm going to call execute. Execute is going to have a percentage, once again, because that is the percentage that the switch has been pulled. And this is also void. So the first thing we need to check is that we have not completed this switch already. So that way, this is kind of the first go through. So if we have not completed and the percentage is above some threshold that I'm going to say is 0.9%, now we actually need to affect the player's sanity. So we need to get the sanity controller here. So we need to do the sanity controller. We need to get tree. We need to, get current scene. And then we need to find our player's sanity controller, and it should be named like that, false or true false. So at this point, we have our sanity controller, and it's always good to do a sanity check. So we want to check if our sanity controller has the method add sanity, just like that. So if the player has the method add sanity, that means we have found the correct sanity controller. Remember, we wrote this right here. So if we can add sanity, then we're going to tell the sanity controller, hey, not add child, add sanity, and we're going to tell it to add the amount of 10 or so. And then we also want to call the sanity controller again, and we're going to want to call its on puzzle complete method, because remember, we just wrote that as well. And you could set these to any values. I'm just going to set them to the defaults because that is what I think is nice and pretty. And finally, we need to say that completed equals true, because on our first go through, when we pull the switch, we want to do all this, but then we want to make sure we never do it again. So let's go ahead and save and test. All right, so we run the game. I'm gonna go ahead and look at my enemy just so my sanity kind of gets down a little bit. All right, so my sanity is pretty low. I'm starting to get distortion. I'm starting to not be able to see my screen. I come over here, fires on, screen turns bright green. And as you can see, we are gaining sanity back to 51. Now, it doesn't really matter if you already have max sanity, it'll still work. If I pull, it'll flash green. And there you go. We now have the makings of a kind of cute, scary little horror game. While we don't necessarily have an enemy with an AI, we do have the ability to drain our sanity. We have the ability to distort our player's screen and have the light in the scene affect what the player's doing. And because we had spent so much time building our interaction controller, it's very important that we built a payoff for that. So maybe you need to move some boxes around, go through some doors, turn a few valves, and pull some switches. And at the end of one of those switches, maybe you give a boost to your player's sanity. So I hope you enjoyed this video. I hope that everything I wrote makes sense. And if anything doesn't make sense, please leave a comment down below. Reminder that this project is on GitHub. I will be uploading a different version than the tutorial we did. It will include more comments and hopefully a better organized feel of the code. So feel free to post on the GitHub as well with any questions you may have. Thanks, and I will see you all in the next one.